Hey everybody, so today we're going to be talking about an interesting topic, which is diffusion. And the big thing that I want to state up front with diffusion is that diffusion models, when it comes to AI, is a completely different breed and separate from pretty much every other area of artificial intelligence. Diffusion is its own unique thing, and like diffusion models operate very differently from other AI models. That's the kind of the big thing that I want to get across is that like from the ground up, diffusion is a completely different process, and this what's called reverse diffusion, which is what AI models use for like image generation. It's all kind of like completely it's more accidental as far as like how exactly it works for image generation, and it's interesting overall because it uh, literally ties into thermodynamics. So let's dive into first of all exactly what diffusion is. And then so diffusion, if you're not familiar with thermodynamics at all, is very straightforward. And then so let's take an instance of a coffee cup, right? Hot coffee, you just pour the coffee into the cup, and then you take a spoon, and you take your spoon straight out of the drawer, and then you put your spoon into the coffee cup. Diffusion is the process of that heat that from your hot coffee transferring to the spoon. When you put the spoon in, it's like room temperature or probably a little bit cold, right? Because it's been in the drawer that you're pulling it out of, and then so you put it in the coffee. All of a sudden, it starts heating up because of that transfer of heat, that distribution, that diffusion of heat is the diffusion process, right? And then so that's just a normal part of thermodynamics. And then so essentially within that you have like physically, like physics, you have different ways that you can like factors that will influence the rate of diffusion. That's the temperature, the properties of the materials, so what exactly it's made out of, and the distance that the heat has to travel. Those are kind of like the three main elements that you can play around with when it comes to this distribution, right? So meaning that like very hot coffee is going to transfer a lot faster to the spoon than lukewarm coffee is going to transfer to the spoon, right? And then also too, if the like transferring from or through, let's say like a ceramic cup is going to be a lot harder than transferring to the metallic spoon, right? And then just and then also too, like if there's a lot of distance and space and air in between, things like that, then that impacts and affects everything overall, right? So very straightforward there. And then so with that said, like this is how diffusion works, right? And then so diffusion is just very simply this heat transfer from hot to cold, like in general, right? It's a heat transfer, a diffusion of heat. And then so reverse diffusion is literally the exact opposite process. And then so this is like there's a lot of images that I could have chosen for reverse diffusion. To me, this is the most symbolic image to look at. And then why are we looking at this particular image? Because what this particular image is showing is differences. The color differences are temperature differences. And then so flat out reverse diffusion is the same as diffusion, where it's based off of thermodynamics, right? So based off of thermodynamics, it's based off of heat transfer. But so in this instance, rather than transferring and looking for that transfer from hot to cold, you look at the groupings of the transfer when you remove the heat, when you bring it to cold. And then so what you have here, the cold that's left represents the images, right? And then so in this instance, like the cold within the pixels represents like a picture of a dog or a picture of a cat or whatever it is that's left over once you remove the heat from the images. And you can do this with sound as well and various other things, not words, right? Text of words you can, but not like the words themselves, which is kind of which is unique, right? But so how exactly does reverse diffusion work? So when a mixture is subjected to a temperature gradient, the particles or molecules within the mixture experience different forces depending on their size, mass, and interactions with other particles, just like with regular diffusion, right? So in some cases, certain particles may be more strongly affected by the temperature gradient than others, and this can cause these particles to move in the opposite direction of the heat flow towards the region of the higher temperatures. So when you see the kind of space differences. As a result, the concentration of these particles becomes higher in the hotter region and lower in the colder region, creating a concentration gradient in addition to the temperature gradient. The extent and direction of reverse diffusion depends on factors such as the size and mass of the particles, the intermolecular interactions, and the specific properties of the mixture. So exactly what you have with the diffusion process, right? And then so in layman's terms, translating this out, what this means is that like a picture of a cat is going to come out through reverse diffusion different than a picture of a dog. There's going to be different elements of it that are hot and cold, and that's exactly how reverse diffusion works, is off of these hot and cold elements, and then essentially denoising the hot and cold elements of an image. And then, so the next concept to understand within this is that all of this is based and derived off of mathematics and off of a singular equation, the diffusion equation. And then, so the diffusion equation is essentially the same for forward diffusion and reverse diffusion. So if you notice here in this, in both of these equations, the forward and the reverse, we can see dx equals f, xt and xt brackets times dt. And then, so we have the fxt in the equation here, and then you'll notice on the reverse diffusion, after the fxt, then you've got a little bit more math that they put in here, right? Starting at the minus g squared, but then you've got the same equation that it ends with, right? So d times t plus g times t times d times w, and then so it's the same equation, but you can add and modify different elements of the diffusion equation. And then so when people are like making improvements of the architecture of diffusion models, this is exactly what it is. They're modifying this equation, but like this equation, it's dx equals f times xt times dt plus g times t dw. Like that's the base diffusion equation. That's going to like, that's always the diffusion equation, right? And so you can add onto it, you can modify onto it, but you're always going to be using the diffusion equation. And then so within the diffusion equation, what you're doing for what you essentially are trying to do within reverse diffusion is you're trying to solve for this equation. And then so by solving for this equation, essentially what you're doing is it's called sampling from the probability distribution, right? And then so sampling from the probability distribution is very straightforward, and that's essentially how all image every time that you're generating an image from like a reverse diffusion model, that's exactly what's happening. So let's say, for example, that you want to generate an image of a cat. And so what the diffusion model does is it samples from the probability distribution of all of the images that it has of cats. And then it's got, and this, like in most instances, it's trained on a lot of images of cats. Let's say 10,000 images of cats. And then out of that, so it essentially, it samples those 10,000 images of cats, and then it comes up with the probability distribution of all 10,000 samples of cats, and then averages that. And then so what you get is the average of that equation, which would be a cat as the output, right? But also within that, that's why you can't control the outputs of diffusion. And this is where a lot of people run into these problems, right? And then you might think like it should be straightforward up front to control these outputs, but you can't control the outputs of a diffusion model specifically because of the math. And so when you see, like, there's been a lot of breakthroughs, especially in the last like year to 2 years with regards towards like AI audio, AI video, and AI image creation, right? But what you're seeing still people are struggling with is getting the these models to output, these image models to output exactly what you want, like exactly what you want it to do, right? So like this image of the dog that we're looking at here on the left, like having a diffusion model reproduce that exact dog on the left is very hard for a diffusion model, because it's, again, every time when you say give me a picture of a dog, it's not going to look at that dog as a reference point. It's going to look at the probability distribution of dogs as a reference point, right? And then so there's no way to tell it, say, hey, just look at the probability distribution of this one dog. That's all I want you to do. But the model doesn't work that way overall. And then so a lot of people don't understand that equation and this equation up front, and then they don't understand why diffusion is so hard to get what you want, like exactly what you want, right? Because it seems like it should just be very easy tweak. Like you can text the model, you can communicate with the model. And so the model, and when you're communicating, when you're prompting these diffusion models, you're not prompting the diffusion element of the model. You're prompting, there's like an NLP portion of the model. So think of it as like if the diffusion there's not a clear analog for diffusion as far as the brain, right? But like as far as a human. But let's say that like LLM models, like and natural language processing, would be the mouth of a human. That's a pretty good analog, right? Let's say that diffusion is the eyes, but it's a really bad analogy. But okay, so diffusion would be the eyes. In this instance, the eyes don't communicate or have any sort of connection to the mouth. Like they're two completely separate entities when it comes to AI overall. And that is especially apparent within like image generation. So what happens is that like when you're prompting a model, so like Midjourney or Stable Diffusion or whatever, you're entering a prompt. So you're telling the NLP model what exactly you want, and then the NLP model translates that and then gives that to the diffusion model. The diffusion model then samples the probability distribution of whatever it is related to the prompt. Let's say that the prompt is I want a picture of a dog. It samples probability distribution of all of the images that it has related to dogs, and then spits out an image of a dog. That's kind of just how that works and functions overall there. So very straightforward overall process, right? So I do want to end and go over one last element of this within this video, which is kind of a new. So within that, right, like the eyes and the mouth aren't connected with regards towards like AI models, and then so that's the big problem that people run into, and that they don't understand is that generally speaking, the mouth isn't connected to the eyes of the model. And then so when you do this process, there's a lot of translation that has to take place, lost in translation, and this isn't doing the same thing as this, right? And then so what we're looking at here is a paper called MoMA, Multimodal LLM Adapter for Fast Personalized Image Generation. And this is a methodology, brand new methodology put out by ByteDance and Rutgers University. Came out earlier this month. And the big kind of breakthrough, and why I'm talking about this paper with regards towards this particular video, is the kind of advancement and the enhancement that they've done. So they have figured out kind of a way to join these two things together. And then so with their particular method, and let's look at I'll show you the images they have here, because that's the best way here. Cool. So what you can see here, and I know that these images are kind of hard to see, so let me blow up this. A little bit too big there. Okay. Nice. Okay, and then so let's talk about these images now. And then so the one on the left is the default image, and then the one right next to the one on the left is the the ByteDance model, like the multimodal model that we're looking at here. And then the ones next to it are like the kind of like best results that you could get from like other diffusion models and other diffusion techniques. And then so what this is kind of clearly trying to show and highlight is that like the ones that are immediately to the right of the reference picture are far closer in reference to the ones like immediately to the left than any of the other ones. And then that's the breakthrough with their process here, right? And then kind of what the breakthrough of their process is, it's just very straightforward, right? So as I said, with typical like Midjourney, Stable Diffusion, etc., you do have the NLP model. So you have the mouth, you communicate with the mouth, and then the mouth translates for the eyes, right? And tells the eyes what to do. And then the eyes just straight up generate the image out. But so what they're doing is saying, okay, so we're going to use the mouth, and then so we're going to communicate with the mouth, and then the mouth is going to produce an output of the image based off of what it recognizes of the image and can describe of the image, and produce an output, an NLP output of the image, essentially. So the like GPT-4, Gemini, whatever LLM model you're talking about, will then take in the image. It will create description of the image, like an output. It will have it will try to construct the image itself, and then it gives that construction to the diffusion model, and then the diffusion model samples from the probability distribution of that construction, right? And then so that's where you can get into very simplistic, like it's a very simplistic way to do it. Let's say you have the picture of the Lamborghini, and then so rather than sampling picture like the probability distribution of all Lamborghinis, then it samples the probability distribution of this Lamborghini, and then so that's how it's able to do it. Same thing with the car, right? This car right below it, I don't know what model, like a Subaru, it's able to, or BMW maybe, it's able to sample the probability of that exact model. Same thing with the cat, the dog, etc. And then so as we go through, that's exactly how this process differs, is it's sampling from the individual probability distributions of the individual images as opposed to all images, which is a huge breakthrough with regards towards all of this. And that's where you might start to see kind of like the ability to get more and tweak these things out more and more, and be able to personalize them more and more as far as like a stable personalization. But overall, I don't think that you're not like, the bottom line that I want to end on with this particular video on diffusion is that you're not going to end up with like extreme personalization breakthroughs with regards towards diffusion. And I don't think, like, my personal opinion is that there's not going to be a huge amount of breakthroughs with regards towards diffusion overall. Again, as I say at the beginning and at the top of this video, diffusion and this whole reverse diffusion process is a very unique process from all other forms of AI, right? From NLP, from LLMs, from machine learning overall. All of that is in a completely different field, completely different mathematical equations, solving completely different aspects and areas. This is 100% rooted in thermodynamics. It's based off of thermodynamics, and it's interesting how it works off of that, because it's literally just using the principles of heat transfer to generate images, to generate sounds, etc. And somehow it works within that, but you don't have a lot of control within that, and that won't change, period. And there won't be any way to change that. So if you like this type of content, please like and subscribe. Thank you very much.